Modern computing operates with billions of transistors packed onto a single processor, but beneath the complexity of 64-bit consumer hardware, the logic controlling it all reduces to a foundational level, the 8-bit processor. This is an Intel 8085. Designed in 1977 using NMOS technology, it stands as an archetype of the 8-bit compute engine. Its 40-pin layout establishes the absolute hardware constraints of early digital processing. To understand how modern embedded systems control the physical world, an engineer must look past high-level programming and master the discrete architecture that makes logic physical. We will start by deconstructing the internal processor core. Then, we will map the external bus systems that carry its signals. Finally, we will see how those distinct components are compressed into a single-chip microcontroller. While today's mobile processors process 64 bits of data at once, the 8-bit architecture remains the baseline for understanding exactly how software instructions manipulate electrical hardware. At the hardware level, 8-bit refers to a processor designed to manipulate data in groups of 8 binary ones and zeros at a time, exactly 1 byte. This diagram maps the 8085 microprocessor. At the center is the ALU, where operations are performed. Tied to it is the accumulator, which holds initial data and stores the final result. For temporary storage, there are 6 8-bit registers, B through L. These can pair into 16-bit blocks. Below them, the 16-bit program counter holds the next instruction's address, and the stack pointer manages memory. Once the program counter fetches an instruction, it is sent to the instruction decoder. This circuit interprets the binary code and triggers the timing and control signals needed to drive the ALU. Notice the limitations of this design. The microprocessor unit is strictly a compute engine. Isolated on its own, it contains no permanent program memory and has no physical way to interact with external devices. To make the MPU functional, it must connect to external memory and input-output peripherals. This requires a physical communication infrastructure known as the system bus. This diagram traces the tripartite bus structure. The 8085 uses 3 distinct paths to interact externally. The first is the 16-bit unidirectional address bus, allowing the processor to address over 65,000 distinct memory bytes. The second path is the 8-bit bidirectional data bus, allowing binary data to flow between the processor and external devices. The third is the control bus, using single-bit synchronization signals to notify hardware of the processor state. Physical space on a 40-pin chip is limited. To fit 16 address lines and 8 data lines, the 8085 multiplexes its bottom 8 pins. Controlled by an external clock, these pins alternate between transmitting the lower 8 bits of an address and 8 bits of data. This rigid bus architecture dictates exactly how and when external memory chips and hardware peripherals can communicate with the central CPU core. Moving binary data across this bus requires the processor to follow 3 precise steps: identify the target address, transfer the binary data, and provide the synchronization signals. This diagram traces a memory read operation. The MPU outputs the 16-bit address 2000 onto the address bus. The external memory decodes it and responds, placing the 8-bit data, 06 hexadecimal, onto the data bus to flow back to the processor. Execution timing is governed by the system clock. An instruction cycle is broken down into machine cycles, like an opcode fetch or a memory read, which are further divided into discrete T-states determined by the oscillator. This timing diagram shows the precision required. During a machine cycle, the address latch enable and read signals align with the square wave clock pulses to ensure the data on the bus is valid before the processor reads it. Software programming is the orchestration of these physical voltage pulses traversing the bus network over highly precise clock cycles. The fundamental limitation of a discrete microprocessor unit is its footprint. Because the CPU, RAM, ROM, and I/O ports are separate chips, they require a complex circuit board with extensive copper traces to carry the bus lines. The solution was integration. Engineers took the processing core, the temporary RAM, the permanent ROM, and the I/O ports, and fabricated them all onto a single silicon die to create a unified integrated circuit. This schematic represents the microcontroller. By moving the memory, timers, and specialized I/O inside the chip boundary, the external data bus is largely eliminated, reducing the physical footprint and power consumption. Introduced in 1981, the Intel 8051 packed ROM, RAM, timers, and I/O ports into one standard 40-pin package, setting a benchmark for 8-bit microcontrollers. This architecture remains active today. The modern ATmega 328P microcontroller follows this integrated design, providing processing power and embedded memory for platforms like the Arduino Uno. In this trade-off, a microcontroller sacrifices the raw computing power and scalable memory of a microprocessor to gain a highly compact design specialized for dedicated embedded tasks. A microcontroller's primary purpose is to constantly react to the physical world around it, measuring variables like temperature, motor speed, or shifting light levels. However, the physical world operates in continuous analog signals, not binary logic. To measure these conditions, the microcontroller requires an analog-to-digital converter, or ADC. This schematic shows the ADC0809 serving as the hardware bridge connected directly to an 8051 microcontroller. The conversion relies on bit resolution. An 8-bit ADC divides a 5-volt reference signal into 256 discrete steps. Every time the analog input voltage changes by exactly 19.53 millivolts, the digital output changes by exactly 1 binary bit. When the ADC translates the analog voltage into an 8-bit binary word, it sends an end-of-conversion signal. The data then flows across the D0 through D7 lines and directly into port 0 of the microcontroller. This interface is the mechanism that translates continuous real-world conditions into the deterministic digital logic required by the core processor. The fundamental architectural difference between these systems defines their utility. A microprocessor expands outward across a complex bus to reach its memory, while a microcontroller loops inward, accessing its own integrated peripherals. Microprocessors are suited for general-purpose computing, where the software environment is constantly changing. Microcontrollers are designed for single-function embedded loops that execute repeatedly for the life of the device. General processors power modern environments that require adaptability and massive computational scale. Conversely, a microcontroller runs a dedicated control sequence, like the logic required for a household appliance. Whether the system uses millions of logic gates or a single integrated chip, the underlying principles of the tripartite bus and ALU operations remain conceptually identical. The specific timing of the system clock and the bidirectional flow of the data bus are the exact mechanisms bridging pure code with physical hardware. By understanding these 8-bit foundations, an engineer moves from simply writing code to orchestrating the physical voltages that drive the modern world.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.